Today we're going to continue with part 2 of our simple machine study. To begin, let's do a quick recap from yesterday. To do anything at all, such as to lift a box, to push a car, to get out of bed, to jump in the air, to brush your teeth, you need to use a pushing or pulling action called a force. If you go around telling people you're strong, for instance, what you really should be saying is that your body can apply a lot of force. You may have watched incredibly strong people on TV pulling trucks or trains with their bare hands, but there's a limit to what even the most muscle-bound person can do. Tools made from metal, wood, and plastic work like extensions to your body, making you feel stronger and helping you work faster and more efficiently. In science, we refer to these tools as simple machines. When you hear the word machine, you probably think of something like a bulldozer or a steam locomotive, but in science, a machine is anything that can make a force bigger. So a hammer is a machine, a knife and fork are a pair of machines, and even an egg whisk is a machine. All these machines have one thing in common. When you apply a force to them, they increase its size as well as apply a greater force somewhere else. You can't cut meat, for instance, with your hand alone. But if you push down on the knife, the long handle and the sharpened blade magnify the force you apply with your hand, and the meat slices effortlessly. When you pound a nail with a hammer, the handle increases the force you apply. And because the head of the hammer is bigger than the head of the nail, the force you apply is exerted over a smaller area with greater pressure, and the nail easily enters the wood. Think about it. Try pushing in a nail with your finger and you'll appreciate the advantage a hammer gives you. Let's recall from yesterday's notes. Simple machines are tools with few or no moving parts that make work easier by allowing us to push or pull over increased distances using less mechanical effort to move an object. And although it seems easier, remember you're actually doing the same amount of work. Simple machines give us advantage by changing the amount of speed or direction of forces. The amount of effort saved when using machines is called mechanical advantage. When we looked at the lever family yesterday, we learned that the lever is one of the simplest machines of all. It's a long bar that helps us exert a bigger force when we turn it. For instance, when you sit on a seesaw, you probably figured out that you need to sit further from the balance point, known as the pivot point or fulcrum, if the person at the opposite end is heavier than you. The further away from the fulcrum you sit, the more you can multiply the force of your weight. If you sit a long way from the fulcrum, you can even lift a much heavier person sitting at the other end, providing that they sit very close to the fulcrum on their side. The force you apply with your weight is called the effort. Thanks to the fulcrum, it produces a big force to lift the load, or the weight of the person. With a long lever, you can exert a lot of leverage. When you are pruning shears, for instance, for cutting tree branches, the long handle helps to magnify the force you can apply. The longer the handle, the more leverage you get. So if you're having trouble cutting a tree branch down with short pruning shears, my suggestion to you is to try using one with a longer handle. When it comes to the invention of the wheel and axle, it basically revolutionized transportation and brought huge changes to society. It's easier to push a cart loaded with a heavy box than to push the same box along the ground because the cart's wheels and axles reduce not only friction, but they also provide us with leverage. Big wheels are used to multiply force in other ways too. Pipes, for example, have wheels called stop valves fitted for them. When you turn the outer rim of a stop valve, the inner axle turns with much greater force, so the pipe is easier to close. Steering wheels work this way too. A truck or bus often has a bigger steering wheel than a car because it takes more force to turn its wheels. The bigger wheel gives the driver more leverage. Wheels can multiply distance and speed as well as force. Bicycles have large wheels so that they go faster. When you pedal, you power the inside of the wheel, but the wheel's outer rim turns around faster and covers more ground. So your pedaling has a much greater effect. Car wheels work the same way. Wheelbarrows combine wheels and levers to brilliant effect. A wheelbarrow makes it easy to transport a load from one place to another for two reasons. First, its long frame acts like a lever, so the load is much easier to lift. Second, it's easier to push the load using a wheelbarrow because only the friction is between the wheel and axle. If you push the load across the rough surface of the ground without using a wheelbarrow, the friction would be much greater. Put 2 or more wheels together and loop a rope around them several times, and you create a powerful lifting machine. We call that machine a pulley. Each time the rope wraps around the wheels, you create more lifting power or mechanical advantage. If there are 4 wheels and the rope wraps around them, the pulley works as though 4 ropes are supporting the load. So you can lift 4 times as much, although the catch is that you'll have to pull the rope 4 times further. Now let's turn our attention to the remaining 3 simple machines to study: the incline plane, wedge, and screw, which all 3 of these are part of the incline plane family. If you've ever helped pull a boat out of the sea, you know it's easier to do if there's a ramp on shore. Instead of lifting the boat vertically, straight up, you get it out of the sea with much less effort if you go up a ramp. You use less force, but you need to pull the boat a greater distance. So you use the same amount of energy in each case. Hill walkers sometimes use the idea of a ramp to get to the top of a steep climb. By zigzagging from side to side across their climb, they effectively create their own ramp. The hill becomes less steep, but they have to walk quite a bit further to get to the top. Ramps are sometimes known as incline planes. An incline plane is a flat surface set at an angle or incline with no moving parts. It allows for heavy objects to be lifted by pushing or pulling the load. Incline planes make the work of moving things easier by allowing us to raise an object with less effort than if we lifted it directly upward. It's important to note that as the incline plane becomes longer, the force needed to move the object becomes smaller. Therefore, the longer the ramp, the greater the distance that is needed to travel, the more mechanical advantage. The steeper the slope or incline, the more near the required force approaches the actual weight. When looking at the ideal mechanical advantage of an inclined plane, we're going to use the same formula as yesterday. Distance of my effort divided by distance of my resistance. The IMA of an inclined plane is essentially the length of the incline divided by the vertical rise, the so-called run-to-rise ratio. The mechanical advantage increases as the slope of the incline decreases, but then the load will have to be moved a greater distance. Again, work in equals work out in an entirely efficient system. Friction will be large if objects are slid across the surface of an inclined plane. To improve its efficiency, you might consider using rollers in conjunction with the inclined plane. The IMA for the inclined plane pictured above is 15 feet over 4 feet, which comes out to approximately 3.8 for its IMA. In order to calculate the actual mechanical advantage of an inclined plane, again, the formula will be the same as yesterday: force of my resistance divided by force of my effort. In this scenario, the force of my resistance is 50 pounds for the cart, and the force of my effort to push that cart up the inclined plane is 20 pounds of force. If I divide those two, I get a value of 2.5 for the AMA of this inclined plane. What is the efficiency of the inclined plane above? Remember to calculate efficiency. It's AMA divided by IMA times it by 100%. And in this case, we would get approximately 67%. Looking at the wedge, a wedge functions as a moving inclined plane that tapers to a thin edge and is used for splitting or raising heavy bodies. Or it could also be used for tightening by being driven into something. Pushing the wedge in one direction creates a force in a sideways direction. The narrower the wedge, or the sharper the point of the wedge, the easier it's going to be to drive it in and push things apart. Therefore, the thinner the wedge, the more the mechanical advantage. But there is a trade-off. To split something apart really wide, you would have to push the wedge a greater distance. In order to calculate the ideal mechanical advantage of a wedge, you're going to need to determine the length, which is equal to the depth of the penetration of the wedge, and divide it by the height, which is the separation of the wedge surfaces. To calculate the IMA for the picture above, we see that the length is 10 inches, the height is 3 inches, so I'm going to take 10 divided by 3, and I get approximately 3.3 for the ideal mechanical advantage of this wedge. In order to calculate the actual mechanical advantage of a wedge, we're going to apply the formula force of my resistance divided by force of my effort. As you can see on the pictures to the right, we're applying 250 pounds of force to this wedge into a surface with a resistance of 700 pounds of force. So the AMA would be 700 over 250, or approximately 2.8. The efficiency of this wedge would be, if we take the AMA and divide it by the IMA, again times it by 100, we get approximately 84% efficiency. And lastly, the last simple machine we're going to look at is the screw. A screw bites into a wood when you turn it around. You often read science books that say a screw is like an inclined plane wrapped around a cylinder, forming the path and pitch. But imagine if you're an ant and you want to climb from the bottom of a screw to the top. If you climb vertically up the outside, you go for a relatively short distance, but it's going to take a ton of climbing force. If you walk up the screw thread winding around and around, you're really walking just up a kind of like a spiral staircase, a ramp wrapped around a cylinder. Yes, you walk much further, but it's a whole lot easier. There's another good thing about a screw. Because the head is bigger than the shaft beneath it, a screw works like a wheel. Each time you turn the head, the sharpened point beneath bites into the wood with greater force. The screw changes rotary motion into linear motion, and it has a large mechanical advantage. Screws with less distance between the threads are going to be easier to turn. So the more threads that a screw has, the more the mechanical advantage. This is because the distance between the threads depends on the slope of the inclined plane. The steeper the slope, the wider the thread. Examples of different screws include jar lids, light bulbs, stools, clamps, jacks, and spiral staircases. Something to keep in mind is that if you're tightening or loosening a screw, if you're using a wrench, the effort arm distance is going to be the length of that wrench. Picture yourself right now trying to loosen or tighten a bolt using a wrench. The applied effort is going to be that distance from the bolt to the wrench. So that will be the distance of the wrench. On the right-hand side, we have some thread information about screws. The first number is always your diameter. The second number is always the number of threads per inch. And the last part gives us a description of what type of thread we're dealing with, coarse versus fine. And we'll talk about the difference between those two on the next page. The distance between the threads is called the pitch. And it's the linear distance traveled by one rotation of the screw. If there's 13 threads per inch, then the pitch would be 1/13 of an inch. Question at the bottom states, how far will a screw with 13 threads per inch move linearly if turned one full rotation? The answer is 1/13 of an inch. As promised, I told you I would talk about the difference between a fine and coarse thread. On the left-hand side, a fine thread screws are going to be preferred choice for hardwoods. Their smaller threads reduce the chance of splitting the wood in a harder stock. So the common types of woods that would require a screw that has a fine thread would be ash, maple, hickory, mahogany, oak, walnut, cherry, or birch. On the other end is a coarse thread. A coarse thread screw is preferred for softwoods because the larger threads create a much stronger hold in the softer materials. Different types of woods that would require a coarse thread would be particle board, plywood, pine, cedar, fir, spruce, basswood, or poplar. The ideal mechanical advantage of a screw is ideally the ratio of the circumference of the screw to the distance that it advances during each revolution. So I wrote here that to calculate IMA, we have DE over DR. DE is going to be one rotation of the effort arm, which is going to be circular, so we're going to look for the circumference. DR is going to be the linear distance traveled during one rotation of the effort arm, which is essentially the pitch. So to calculate the IMA, it's going to be the circumference divided by the pitch. And at the bottom it says, what is the IMA of the screw above if effort is applied by an 8-inch long wrench? So the IMA would be 2 pi r divided by the pitch. So 2 pi times 8 inches divided by the pitch of 1 over 20. And we get an approximate IMA of 1005. And to calculate the screw's AMA, we're going to apply the formula force of my resistance divided by force of my effort. So here, the force of my resistance is 1,200 pounds, and the force of my effort to rotate that screw is 35 pounds. When I divide those two values, I get approximately an AMA of 34. The efficiency of the screw would be AMA over IMA times it by 100, and we get a very low efficiency of 3.4%. And if you're wondering why the efficiency is so low, think about it. When you screw something into something, such as a wall, there's going to be a ton of resistance and friction. So that's going to decrease the efficiency. So that's pretty much it for the science of simple machines. Once you understand how machines work, you're going to start seeing them everywhere. Even your body's packed with the different types of machines. Your skeleton, for example, is a collection of levers. So when you get a chance, take a look around your home and see how many more simple machines you can spot. You'll be amazed at how many you can find.